Welcome back. This is the second video in the playlist that deals with chemical equilibrium. Now, for a short review on where we ended up in video number 1. So, in this case, we're looking at a chemical reaction where the reaction is initiated with 1 atmosphere of iodine combined with 1 atmosphere of chlorine. And I had mentioned that there are two main things that you've got to wrap your mind around before we really get into the nitty-gritty of equilibrium. The first is the idea that most chemical reactions actually don't go to 100% completion. So what I'm showing here in this little table is that after the reaction comes to a dynamic stop, if you will, and I'll come back to that concept, you can see that the concentration of iodine and chlorine has not decreased to 0. In fact, it's decreased to about 0.2 atmospheres in each case. The product, the ICl, has increased to a pressure of 1.6 atmospheres roughly, and you can see that that's depicted on this graph over here, where at the start of the reaction, at the point where there's no ICl, that the concentration increases and reaches an asymptote. So it approaches 2 atmospheres but never actually reaches that quantity of ICl, and the pressure of the iodine and the chlorine decreases as you would expect in a chemical reaction, because these two components are the reactants, but they do not decrease to 0. In fact, they reach a pressure that's around 0.2 atmospheres, a little bit less than 0.2 atmospheres, and the products reaches a pressure that's just a little bit over 1.6 atmospheres in partial pressure. In the last video, I emphasized the fact that what controls how far a reaction goes is the delta G naught, or the thermodynamics for a particular chemical reaction. And in this case, the thermodynamics, the delta G is equal to a minus 10.9 kilojoules per mole. The magnitude and the sign of the delta G is what determines what the fraction of products versus reactants is going to be in a chemical reaction. And that was the second major thing that I had introduced in the first video. Down here on the left is a number line that represents the different options for the thermodynamics. And in the example that I'm showing above here, we're in a scenario which is down on this end of my number line. So the delta G naught is negative 10.9 kilojoules per mole. The fraction of products when the reaction comes to a dynamic end is greater than the fraction of reactants that are present in the reaction flask. By the same token, if we had been dealing with a chemical reaction that had a large positive delta G naught, then the fraction of reactants would be greater than the products in the reaction mixture. And when the delta G naught is plus or minus but close to 0, this is a situation where the equivalent proportionality of products versus reactants is going to be very similar. And these are going to be reaction mixtures that are going to have large amounts of both products and reactions present in the reaction mixture once we reach equilibrium. I don't want to say here that the products are going to equal the reactants, because that would be incorrect. But we will have a proportional equivalence of products versus reactants that at equilibrium when delta G naught is plus or minus close to 0. And that proportional equivalence is going to depend on what the coefficients are in the balanced chemical equation. So the magnitude of delta G, the size of this value and its sign, determines the extent at which a reaction given a mixture of reactants is going to shift to the right. Now, in this video, what I want to do is talk about this proportionality that we have once the reaction has reached the point where we're to the right of the blue line here, where we're to the right of this blue vertical line, this place where the asymptote, where literally the rate of the forward reaction is equal to the rate of the reverse reaction, and that's emphasized by the double half arrows here. And once we reach that point, then the proportion of products versus reactants reaches a constant value that can be represented, and now I'm going to define what we call the law of mass action, the law of mass action. And we're going to define this by defining an equilibrium constant, capital K. In this case, I'm going to define it two different ways for us right now. First, I'm going to define it as Kc. And this is going to be based on the proportionality of reactants versus products and I'm going to write a generic chemical equation here. So we have reactant A plus reactant B to produce reactant C plus reactant D, where each of these reactants has a unique coefficient like we would in any balanced equation. And when we write the equilibrium constant for this, it's going to equal literally the products divided by the reactants. So we're going to have the concentration of C raised to the C power times the concentration of D raised to the D power divided by the concentration of A raised to the A power times the concentration of B raised to the B power. So for the chemical equation in question here, we're going to write the equilibrium constant for this. Now, I defined our law of mass action in terms of concentration. That's what this subscript C means here. Notice that in this reaction, though, we're in partial pressures. So we're going to define our equilibrium expression in this case in terms of a Kp. And the Kp is defined exactly the same way as a Kc, except that we're going to define this ratio in terms of partial pressures. So how this would look different would be in the following way. It would be partial pressure of C raised to the C power times the partial pressure of D raised to the D power divided by partial pressure of A raised to the A power times the partial pressure of B raised to the B power. So now applying, and again, the subscript P here is because we're in units of partial pressures. So now let's go ahead and define our equilibrium expression, or our law of mass action. So this is what I call an equilibrium expression. It is the ratio, literally, of products to reactants, compensating the products for the stoichiometry of the equation, the balanced equation, and it is equal to an equilibrium constant, which is a number. Now, because we're plugging either concentrations or partial pressures into this, you can see that we are going to end up with units, but equilibrium constants, this number, I'm going to circle this number that we end up with, we drop the units, and the only thing that matters with an equilibrium constant is the number itself. In other words, the magnitude of the number is what matters. Magnitude of the number. The size of the number is what's going to matter. So now when I come back and we're going to write the equilibrium expression for the equation that I'm showing above here, and I'm going to write it as a Kp because we are in units of partial pressures. then it will be written as the partial pressure of ICl, and this is going to be raised to the second power because of the coefficient in the balanced equation. All right, and it will be divided by the partial pressure of I2 raised to the first power times the partial pressure of Cl2 also raised to the first power, because the coefficient for the I2 and the Cl2 is 1. Okay, now if we go ahead and we calculate what this value is going to be, and let's see, I'm going to squeeze this in. I apologize for doing this, but I'm going to squeeze this in. So if we go ahead and we calculate this value, the Kp for the reaction as it stands here, the one I'm demonstrating, is going to be 1.638 atmospheres, and this quantity is squared, and it will be divided by 0.181 for the I2 times 0.181 for the Cl2, and when we crunch the number, what we end up with is an equilibrium constant that's going to be equal to 81.9. 81.9. Now, as I close the video, here's what I want to point out. We have a delta G naught, which is minus 10.9 kilojoules per mole. It's negative, and it's a respectably large value. Notice that our equilibrium constant is also a fairly large number. So the proportion of products divided by reactants, products over reactants, is 81.9 to 1. 81.9 to 1. This means that the fraction of products at the point where this reaction comes to a dynamic stop, the place where the forward rate of the reaction is equal to the reverse rate of the reaction, that the products in this reaction are greater than the reactants in the reaction mixture. So in finishing, we can add some information to our graph down here, or the number line. So for reactions that have delta G naughts that are negative and large, K is going to be greater than 1. For reactions where delta G naught is plus or minus close to 0, so this range in here, K is going to be approximately 1. And for delta G's that are positive and large in magnitude, K is going to be less than 1. Okay, and the products, or excuse me, the reactants are going to be greater than the products. The concentration of reactants will be greater than the concentration of products at the point of equilibrium. All right, and with that, I'm going to go ahead and close this video.